This is part 8 of reading COVID wastewater data. We're going to be focusing on this publication by the people that run Wastewater Scan, looking at storage conditions of COVID RNA quantification in wastewater solids. First, we want a little bit of wastewater basics. So the primary sedimentation chamber is right here, and that's where we're going to be pulling our solid wastewater, which is a part of our influent system, which is the inflow side, versus the effluent, the outflow side. And then of importance to note, there's the liquid phase, and then there's also a solid sedimentation that builds up at the bottom. So starting off, a wastewater surveillance program should provide rapid turnaround for sample measurement, ideally within 24 hours. However, sometimes sample storage is necessary for a variety of reasons, including biobanking. And that in this study, they found that a short-term storage of 7 to 8 days at 4 degrees Celsius, so this is refrigeration temperature, has little effect on the measured COVID concentrations, whereas longer-term storage at refrigeration temperature between 35 and 122 days of freezing reduces measurements by about 60% on average. And interestingly, there's a pepper-mild model virus, PMMOV, that's typically present in wastewater, so there's historic data on that. So the decay curve of that can be normalized, so you can use that as like a correction factor, since we have a lot of known information about that, to correct for these reductions to see what it should have been or would have been otherwise. And also that COVID RNA in solids during freeze thaws is less than those reported for the same target in liquid influent by several authors. So pulling samples from that solid sedimentation at the bottom of the tank is going to be more consistent and have less effects on storage than it would if you're pulling from that liquid phase that we showed. And interestingly, for that liquid influent, they determined that storage and freeze thaw, so that can reduce the measurement concentration on an order of magnitude. So when we think of magnitudes, we think of a scale of 10. So basically, it would be, if it was 100 concentration, it would be reduced by order of magnitude. So it would chop off a 0, that would be 10. So in that case, it would be a tenth the concentration. And if it were 1,000, the concentration, it would be an order of magnitude smaller. So it would go from 1,000 to 100. So how they're doing this is they're taking the settled solids, they're storing it at 7, 8, 35, 91, or 122 days at refrigeration temperature, or storing it 2 to 3 days at negative 20 degrees Celsius, and also looking at longer storage times at negative 80 degrees Celsius. For molecular targets, they're looking at the N gene, S gene, and ORF1A gene. So they're looking at things like the spike protein, the nucleocapsid protein, and then this section of the COVID RNA genome, where the most easily understandable results are actually in table form as opposed to graph form, where compared to testing samples right away within 6 hours of collecting them, there's no difference between the 7 to 8 day samples. However, when you're refrigerating for longer periods of time, you have about a 60% reduction in those values. And then even just freezing for 2 to 3 days at negative 20 degrees Celsius, you have again those about 60% reduction of the baseline values. And then if you're storing at negative 80 degrees Celsius for a long period of time, that seems to be better at preserving it. So it's better to store at those colder temperatures to not get as much die off. So it's about, I'd say like 65-70% on average here. But interestingly, that virus we talked about earlier, that model virus, it is decaying at about the same rate. So by adjusting for the factor of this very known sample of virus decay, we can correct for these to get the baseline value back. And that's how sample storing conditions can impact wastewater quantification for COVID.